Well, good afternoon, everybody. My name is Andrew Jenkins, and I am the Planetarium Manager here at Lancaster University for the L Universe or Luniverse Planetarium. And today I'm going to be taking you on a tour of our night sky so we can have a look at how things are changing. So, of course, space is an incredibly interesting place, but it is permanently and constantly changing. From our sun to distant stars, nothing about our view of the universe is constant. Everything is either moving, evolving, or changing in some way that is totally different. And as our understanding of the universe deepens, we're becoming more aware of how varied space is. And as we delve into this exciting world, it makes perfect sense to start with something that we can all do, which is observe our own night sky. So this is what you'd be able to see from the UK today. Obviously, that depends on how your weather is currently. Ours is all right for a change in Lancaster. It's not too bad today. Bit grey, but it's not raining, so that's a nice change. But no, this is a very optimistic look of what weather in the UK could look like. And because this is a full planetarium suite, I'm able to speed up time, which is a very convenient process that I sometimes wish I had in real life. And I can turn our daytime into nighttime, and we will have a look at what you will actually be able to see tonight when the sun sets. Again, from UK skies and realistically the Northern Hemisphere. Now, what I've actually got here is also the simulation of the light pollution that you would experience in Lancaster, or at least as close as I could reasonably get it. So, although the viewing location across the entirety of the UK is pretty much going to be the same, we're quite a small country. The variation in a night sky doesn't really change depending on where you are. All the way from the Highlands down to Exeter, you're going to have pretty much the same view. But the light pollution of those two places are going to be very different. And that can massively affect what you're able to see. So from Lancaster, you're going to have a pretty decent view, especially if you're just on the outskirts of the city. This is actually not optimistic, but a reasonable estimation as to what your night sky would look like. And there's quite a lot you can actually see, especially tonight. If you go out, you can see Orion just before it sets, so around 10 p.m. or so. Mars as well is still visible. Ursa Major is certainly the constellation Ursa Major. So the Plough, the Big Dipper, you look straight up, that one's nice and visible as well. All of these things, super easy to spot at the moment. But if you go to other parts of the country, sadly, this is not the case. Our ability to see the sky is dependent on where we are, and it changes our observations. Let's take the extreme example of London. Yeah, it's nowhere near as good. So those beautiful stars and the majesty of our night sky can be completely obscured by streetlights, buildings, construction work, industrial plants, all those sort of things that produce light, typically on quite a large scale, makes it very hard to see our night sky and changes our ability to do deep sky observations as well. It's why telescopes sit in different places in the world, typically as remote as humanly possible and very high up as well. So there's less atmosphere. Atmospheric turbulence also makes observations really difficult. It's quite a shame, really, because it means that good chunks of the country and definitely big parts of the world miss out on the chance to see truly dark skies. However, there are parts of the UK where it is amazing to go stargazing. We have beautiful national parks, and some of these national parks have remarkable dark sky status. Kilda is one that always springs to mind, as it's actually an internationally recognized dark site. And if you go, you will actually get skies probably more similar to this. Yeah, really, really rather spectacular and absolutely wonderful to go and experience if you ever get the chance to. Fab stuff. I'll bring us back to daytime, because what's actually happening here, the reason why we have so much difficulty in seeing our night sky and how it changes depending on where you are, is actually due to our atmosphere. So the reason you can't see other stars during the daytime is, of course, down to the sun, but it's the reflections and refractions of the sun's light in our atmosphere that makes it very, very difficult to see things. If we didn't have an atmosphere, then our daytime would always, every day, look like this. And that is what you'd be able to see outside all day, every day, if we didn't have an atmosphere. You'd also die within about 3 seconds. But it's quite pretty. So, swings and roundabouts, swings and roundabouts. Anyway, considering we've already started our little tour by having a chat about our sun, it only makes sense that we start our tour by talking about the sun itself and how that changes over the course of a year. Now, you might all, of course, know that the sun's position in the sky isn't constant all year round. It changes as the seasons go. That is because of the tilt of the Earth. The Earth is tilted from its axis by 23.5 degrees. I'll just reset that because it's a planetarium and it's always a little fiddly. Cool. So yeah, the tilt of the Earth affects how high in the sky the sun is and therefore affects our time of day. So what you're seeing right now is the sun set to UK GMT position roughly in February. I believe this was set to, and this is midday. So this is midday in February. As we all know, pretty cold, and the sun is really low in the sky. That's about as high as it's going to get. Really kind of rubbish. But something you don't normally get to see is how different the sun looks at different parts of the world at the same time. This is a planetarium. I have that power, and we're going to explore it now. So this is what would happen if you were able to run down the Greenwich Meridian line at pretty fast speeds. So what I'm doing effectively is changing our viewing position from Lancaster, bringing us all the way down towards the equator. And as you can see at the equator, our sun is much higher in the sky than it is at Lancaster. So what I've done here is not change the time of day. It is still noon, according to our planetarium, but this is what noon in the equator looks like during winter, as opposed to what it looked like in Lancaster during winter. Why on earth am I living here? So much nicer. Of course, this is true if you keep going. Eventually, you'll reach a peak where the sun is the highest it possibly can be, and then it will start falling back down towards the poles, towards technically the north in this case, as you hit the poles. So this is what the South Pole looks like during its summer. What's really, really cool about this is that during our winter, the South Pole, Southern Hemisphere, of course, is experiencing its summer. And the change here is that during a South Pole summer, especially its peak, the sun doesn't set. The tilt of the Earth is actually so much, the sun never dips below the horizon. So as I speed up time here, which makes the sun and a day take only a couple of seconds, you can see how the sun never drops below the horizon. In essentially what is like a 360 view here. So let's say you had one of those 360 cameras and you zoomed out, you can see how the sun never dips its way below the horizon. How cool is that? I'll show it from another view, only because I really just love this idea. Is that even on our own planet, the differences in our ability to see and understand things can change so wildly, which I really, really enjoy. This is actually also another really good way to remember that it's not the sun that moves its way across the sky, it's us that rotates, especially if I do this. I really love that button. It's so much fun. Cool. Right, time to go and see the sun a little bit closer than we have so far. Now, the sun, largest object in the solar system, of course, it is 99.9% of the weight of the mass of the entire solar system. In fact, it is 1,305,693 times heavier than the Earth. So it's pretty big. It's pretty big. What's amazing is that the sun is actually so far away from us that if it was to suddenly disappear, it won't, but if it was to suddenly disappear, it would take us 8 minutes to even notice. And that's not because we're not observing it, we're observing it all of the time, it's because light takes 8 minutes to travel from the sun through space and to reach us. So even on the scale of our solar system, distances are large and their effects are quite noticeable. The surface of the sun, as you can see here, are covered in spots, regions of the sun that are a little bit colder than the surrounding area, and each one of them is roughly the size of the Earth. Hopefully that gives you a bit of scale here. Yeah, the sun's pretty big. Now, the reason the sun has these spots is because parts of its magnetic field get bunched up, which stops heat being able to rise from the center so easily. It slows its convection currents down a little bit, and therefore the areas are a tad colder. Now, the magnetic field lines around a sunspot can get very easily tangled. And when they do, they undergo a process called reconnection. And reconnection typically shoots out a very, very large amount of energy, which we would then call a solar flare. in this case, or if it's big enough, a coronal mass ejection. What's awesome about this is that we can actually use the number of sunspots to track how the sun is changing over its 11-year cycle. So over the period of 11 years, the sun's magnetic poles flip. The north becomes the south and the south becomes the north. Whoop. In the process, the sun will become more or less volatile. So as the poles are really starting to shift from one to the other, lots of tangled field lines, large number of sunspots, quite a large number of solar flares, mass ejections, that sort of stuff. And then they'll settle back down when they reach their respective poles again. This number of sunspots is directly linked to the volatility of the sun. So by tracking the changes in the number of sunspots, something that's been done by humans for literally hundreds of years, we're able to make sure we can track the changes in our sun. Pretty amazing. And this is obviously over a lifetime that's actually fairly easy to observe, right? 11 years, that's something that we can handle. If you ever wanted to do your own bit of sunspot spotting, obviously you need specialist equipment. Do not stare at the sun. Can't say that one enough. A pair of binoculars that aren't made of plastic, that metal and glass ones, and a piece of paper. Really good. Do not look through the binoculars directly, but if you set them up so that they project onto a piece of paper, that could be an impromptu sunspotter. And you can actually track sunspots over multiple days because the sun rotates with a period of about 25 days or so. So you can actually see them move across the sun, which is really cool as well. Additionally, changes in the sun. The sun will die at some point. Fortunately, not tomorrow. It's in about 5 billion years or so. Not a scale that we can observe directly. The sun has existed so far for about 4.5 billion years, and it's got another 5 to go. When it does die, though, it's going to be pretty devastating for the Earth. The sun will become a red giant, which means it will expand in size astronomically. In fact, it will become so large, it will almost certainly engulf the Earth. And to show this, I've thrown together a little animation. Now, please note, this is just sort of a scale animation. These things are to scale, and I've used a red supergiant, Betelgeuse, or Betelgeuse, or Betelgeuse, depending on who wants to pronounce it, as my scale here. But it's a nice little representation of how big the sun might get during its death process, essentially during its red giant phase. So this is the sun right now, and this is it in comparison to Betelgeuse. Yeah, it's pretty big. I'll make it a little bit easier and I'll zoom it out for you. I just at this point to remember that we're a dot in comparison to the sun at the best of times. So in this, we are but a speck. We're not a visible thing. Our entire existence is a little dot. I love space. So yes, during the sun's death, it will undergo quite a few different phases. It will become a red giant. As it expands, it will keep expanding, contracting over a couple of different cycles, eventually generating very large solar winds, blowing off the outer layers and leaving behind a white dwarf star. So lots of changes to come for the sun. Fortunately, not for a little while. All right, that's enough of the dead sun. We'll head back to our planetarium. And in fact, we'll head over to something maybe a little bit... Oh, I left in my number for me. That's kind of myself. We'll head it over to something maybe a little bit closer to home, which is going to be our space partner, the moon. Now, of course, we all know about the changes in the moon, the phases of the moon from new moon to full moon. Nice, easy one to observe for most of the year, as long as it's not cloudy. That's kind of an obvious thing to talk about. So instead, we'll talk about how the moon came about. Well, the generally accepted view is that 4,510,000,000 years ago, another planet called Theia smashed into the Earth. This massive collision caused Theia to combine with the Earth and splatter rocks out into space. And these rocks then combine in further collisions to eventually form our moon, which actually means the moon has a little bit of the Earth in it, making it a closer partner to us than you might have originally thought, which I think is really cool. The moon's also changing because it's actually slowly moving away from us. In fact, it's moving away from us at 3.78 centimeters per year, although estimates, of course, vary massively. The moon disappearing slowly is actually going to be quite a concern. Not in our lifetimes, we're talking millions of years once again, but as many of us know, the moon controls our tides, which will mean massive changes to the way in which our water interacts with our land. Obviously, that's happening on a grand scale on this planet anyway, and I think will probably do a lot more damage than the moon will, but it's worth bearing in mind that some of the stability offered by our space partner won't always be there as it slowly, very slowly drifts away from us. So, enjoy it whilst it's here. On to another planet where our understanding of it is constantly changing, is one that always seems to capture everybody's imaginations. It's Mars. Of course, Mars has been in the news very recently with the Perseverance landing, which if you've not watched, I cannot recommend it enough. Actually seeing a full-length video of a rover landing on another planet is one of the most amazing things I have ever seen. So do go check that out if you've not already seen it. I won't play it as it's NASA's own video, but do look it up. But Perseverance's job is to help change our understanding not only of Mars, but of the universe as a whole. Perseverance's job is to look for previous signs of life. So it's been sent to a dried up lake bed, which what we believe to be a dried up lake bed. It has got a probe that will drill into the surface and look for fossilized examples of life. So not current life, but life that may have once lived in this lake, for instance. What's really amazing is the process in which we're going to do some of the analysis on this. So Perseverance, this is so true and I love it. Perseverance is going to drill into the soil and put the sample into a little tube. It will then drop that tube onto the surface, basically. Boop. Later, the European Space Agency is going to send another rover to go pick up those samples, pop them into a little rocket, and then fire them into orbit around Mars. Whilst in orbit around Mars, another satellite is going to pick it up and then fire it back towards the Earth. When it reaches the Earth, it's going to be dropped into our atmosphere and slowly fall down to reach the planet again, meaning scientists here will be able to analyze it. So to recap, that's drill, put in tube, drop tube on floor, pick up tube, put in rocket, go in orbit, pick up from orbit, fire to Earth, hit the atmosphere, get back home. Quite a little process there. The earliest estimates that I've seen for this actually being complete is about 2036. So quite a while away, but a very exciting change there. Especially because if we do find previous signs of life, that means we know conclusively for the first time ever that we weren't alone in the universe, or at least there is the potential for their life to exist elsewhere in the universe. And it will undoubtedly be one of the greatest scientific breakthroughs of this century. Another really cool change that's actually taking place at Mars is one of its moons is undergoing some sad processes. Mars has two moons. They're called Phobos and Deimos. And Phobos is actually starting to fall apart. And in 40 to 50 million years or so, granted not very quickly, but in 40 to 50 million years or so, it will actually be destroyed by Mars's gravity and form rings around Mars very similar to those rings around Saturn. Pretty awesome. Pretty awesome. But enough on the planets for now. We'll talk about something else. Stars, something I love to talk all about. And specifically, we're going to have a little chat about my favorite of all the stars, except from our sun, which has to be Alpha Centauri, or Centauri, depending on how you like to pronounce it, which is this sort of white big one in the middle here. Sadly, this is as close as I can get with our Planetarium suite. I mean, realistically, it would just be a white splodge. Now, Alpha Centauri, if you don't know, is the closest visible star to us. It is 4.3 light years away, which means it takes light 4.3 years to travel from this star to reach us, which is actually an incredibly long distance. For scale, let's say you stole the Saturn V rocket. So that's the rocket that took astronauts to the moon. How you managed to steal a rocket from a museum and get it working, again, we're going to ignore, but you've stolen this rocket and somehow you set it up and you're flying towards Alpha Centauri and you don't have to worry about fuel consumption and you're just going to go. This is the fastest human beings have ever gone by quite a long margin. And if you're flying straight and non-stop towards Alpha Centauri, my estimation is that it would take you roughly 150,000 years to get there. Yeah, 150,000 years, which might just be a little bit too long to make it our next destination. The reason why this is so important is because I just want to emphasize the importance of sorting out things here on Earth. When we talk about change and all these lofty topics, it's quite easy to forget about the planet we live on. And a question I'm asked over and over again is, what planet would you love to live on other than the Earth? And I always answer in the same way, none of them. Every other planet in the universe that we're aware of is desperately trying to kill us. Mars is inhospitable, Venus spits acid rain on it, Jupiter is literally a ball of gas. We are very suited to live on this planet. We can't just go and visit another solar system. The technology to do so doesn't exist. And whilst faster than light travel theoretically could become a thing, we have literally no idea of how to actually do it. So whilst it's a lovely thought that maybe we could go and colonize the rest of our solar system, the rest of our galaxy, considering our nearest neighbor is this far away, 150,000 years, very unlikely. So changes on this planet are fairly permanent. And if we don't address them, well, I'm very sorry to say, we can't just fly to another place to go sort them out. Always a good one to bring up. But finally, I'm very conscious of time, so I won't go on it too much. We have Proxima Centauri, which is slightly closer than Alpha Centauri, but it's not visible through your eyes. So I don't think it's anywhere near as cool. It's a really good justification there. Additionally, something that is worth observing in the night sky, if you ever get the chance to go look at a clear sky, of course, are the constellations. I referenced the 88 that are accredited by, which one is it? International Astronomy Union, I believe, have the 88 internationally recognized constellations. But even these things are not static and stable. They will change over time because they are actually stars that are moving. They're moving very slowly, but over the course of hundreds of thousands, if not millions of years, all of our constellations will look a little bit different because they're going to move. Additionally, our view of the constellations is entirely dependent on our position in the solar system and the galaxy. And I'm going to try and switch over to another program to show you what I'm on about. Lovely. It's always good when that does actually work. So this is another view of the constellations. So for example, here is Ursa Major, so the plough, the Big Dipper. There's the handle, there's the saucepan bit, that's the plough. Great constellation, definitely my favorite. Nice and easy, that's what we recognize. Now, of course, the whole point here is that constellations aren't 2D objects, they're 3D objects that are being viewed in a 2D viewing window, I guess is the best way to put it. They have depth to them. Some stars are much closer and some stars are much further away from us, which means if we slightly change the position in which we view the constellations, well, then they're going to look very different. And this is a great way to show that. So hopefully I can show you what I'm on about. Like so. So if I just move our position a little bit, you can suddenly notice that the constellations look very different. Yeah, the plough doesn't look as much like the plough. In fact, if I really zoom this out, you can see how different the distances between the stars that make up our constellations actually are. They are incredibly deep 3D objects. I say incredibly deep, obviously on the viewable spectrum, but they're not these nice flat images. They are 3D, which means where you look makes a big difference of how they look relative to you. So as I move around here, you can see how something as static as a plough actually changes, which I think is amazing. Another good one is Canex Venatici, which is literally two lines that somehow represent a dog. I won't go there again, but that, again, looks very different depending on your viewing angle. Not something you need to worry about from Earth, but a good change that I love to point out when I get the opportunity. So, of course, there are many constellations, and I would go into the details about lots of them, but I am so conscious of the time, so I think it would be best for my talk to end here. Thank you ever so much for listening, and I hope you really enjoyed learning a little bit more about some of the changes that are taking place in our own solar system, as well as deeper into the sky.